In this lecture, we'll be looking at section 4.3, which is entitled the binomial distribution. The binomial distribution is a special probability distribution that corresponds to a certain type of probability experiment. And those probability experiments are called binomial or Bernoulli. We're going to call them binomial. And the first thing we want to do is get a feel for what constitutes a binomial probability experiment. So here are some of the characteristics. First, a binomial probability experiment has a fixed number of repeated trials. So there are actually two pieces to that. The easier part to understand immediately is that we're repeating the same thing over and over and over. Think of flipping a coin many times, rolling a die, asking the same question to many people. You've got these repeated trials. You're doing the same thing over and over. A more subtle part is that that number of trials is fixed. So you know exactly how many times you're going to repeat the experiment. We'll look at a couple of examples where we see what it means for the number of trials to be fixed or for the number of trials not to be fixed. We'll distinguish between the two. Quick bit of notation here. The number of trials is usually denoted by n. And that's a natural notation because it's very similar to a sample size. It's the number of times you're going to repeat the experiment or the number of individuals in your sample who you're going to get some information from. Secondly, and where the bi and binomial comes from, the outcomes can be categorized into one of two types. So there are these two buckets that we can place all of the different outcomes into. And we typically give them names. We call them success and failure. This has nothing to do with good or bad, happy or sad. Success is the thing that you're looking for, and failure is the other category. And the last characteristic is that the trials are independent of one another. That means what happens on one trial does not affect what happens on future trials. There's no consequence of a previous outcome for future outcomes. They're independent of one another. And I'll give an example of where that does not happen as well. Let's look at a few examples of experiments and we'll explain why it is or isn't binomial. So my first example on this slide here says that a die is rolled 3 times. And if you just stop there and think about the experiment of rolling a die, you might think, well, this can't be binomial because the die has 6 sides on it. But depending on what the random variable is, this might still be a binomial experiment because we're not saying that there are only 2 outcomes. We're saying that there are 2 categories of outcome that we can put these into. And you can see that the random variable that I've chosen is the number of 6s rolled. So now we have these 2 buckets. You either roll a 6 or you don't roll a 6. So let's go through all of the different characteristics here. Are there a fixed number of repeated trials? Yes, we're going to roll the same die 3 times. Repeated trials, fixed number of trials. Secondly, can the outcomes be categorized into one of 2 types? Yes, you either roll a 6 or you don't roll a 6. So one choice would be to make a success rolling a 6, and a failure would be not rolling a 6. 2 categories of outcome, 2 classifications of outcome. And lastly, are the trials independent of one another? Sure. When you roll a die, it doesn't matter what you got on the previous roll. Future rolls are independent of the previous roll. The die doesn't remember what you rolled previously and try to force itself to a new side. That independence is the most subtle one. So let me give you an example of an experiment where the trials are not independent of one another. The non-example on this slide says our experiment is to draw 3 cards from the top of a deck one at a time, and our random variable is the number of red cards. Now we do have a fixed number of trials because we're going to draw 3 cards. We do have 2 categories of outcome because you either get a red card or a black card. We're good there. But the one I want to focus on is the independence. And these trials are not independent of one another. What happened on a previous trial affects what could happen on future trials. If we draw a red card off the top of the deck and we don't put it back, there are now fewer red cards in the deck and the probability of drawing a red card the next time is less than it was the previous time. And if we draw a black card off of the top in our first draw, then the probability of drawing a red card is larger than it was in the first trial. These trials are not independent of one another. What happened on a previous trial affects probabilities, affects future outcomes. And so these are not independent of one another. Now, before you get worried about that, because it can be subtle or tricky, you'll never have to wonder if the trials are independent of one another. It is an important aspect. I want to make sure that I cover it. But on graded material, if you've got an experiment where there are a fixed number of repeated trials and where the outcomes can be categorized into one of two types, you're going to be allowed to assume independence. Let's look at another pair of example and non-example. Here's an actual binomial experiment at the top. The experiment is a random sample of 100 people are asked, does pineapple belong on pizza? Now, this is different than the types of probability experiments that we've been discussing in the class so far. Most of our experiments have had to do with flipping coins, rolling dice. But this is a probability experiment as well, and the probability comes in because we grabbed a random sample of people. Depending on which people we select, we're going to get different outcomes of this experiment, and that's where the randomness comes in. That's where probability comes in. I've made the random variable the number of people who say yes. It could just as easily be the number of people who say no. Let's see if this satisfies all of the characteristics of a binomial probability experiment. We have a fixed number of repeated trials because we're going to select exactly 100 people. That's fixed. And we're going to repeatedly ask the same question over and over to 100 people. Secondly, can the outcomes be categorized into one of two types? Sure, there are people who say yes and people who say no. This is a much more obvious example. And even if you want to be a smart aleck about it and say, well, there are some people who will say it depends, well, then we still have two categories. There are the people who say yes and the people who don't say yes, regardless of what their other answer might be. We can still categorize this into two. So to play it safe, I might say that a success is a person who says yes, and a failure is a person who does not say yes. And then I'll be able to step over any of your semantic landmines. And lastly, are the trials independent of one another? If we grab a random sample of 100 people, then there's no reason to suspect that the answers of one person will influence the answers of another person, or that these answers are inherently linked somehow. If we were to grab 100 people using one of those bad sampling methods, like a convenience sample or a volunteer sample, then maybe there might be some inherent bias to our sample, and they might not be independent of one another. Like if you ask a bunch of your friends, or if you ask a bunch of people who live in the same town, who all eat at the same pizza place, those could inject biases. Those might not be independent. But if we grab 100 people at random, it's a safe assumption that the trials are independent. I want to do another example that might appear to be binomial, but isn't. The experiment is a coin is flipped until you've seen 8 tails, and the random variable is the number of flips. I want to focus on what I think is the more obvious characteristic that makes this fail being a binomial probability experiment. It's actually a second subtle one that you might notice as well. But the obvious one to me is that we don't have a fixed number of trials. It doesn't say we're going to flip the coin 8 times, which would be a fixed number of trials. It says we're going to flip the coin until we have seen 8 tails. And that's not a fixed number of flips. That might take exactly 8 flips if we get really, really lucky. It might take 20 flips. It might take 30 flips if we're really, really unlucky. There's not a fixed number of trials here, and so this isn't binomial. Now, spending all of this time talking about how to identify binomial probability experiments begs a question. That's who cares? Why would it matter if an experiment is binomial or not? Well, it turns out if you can identify an experiment as binomial, there's a special probability function that will allow you to calculate the chances of a specific event in that experiment without having to write out the sample space. And this is really nice when the sample space is really, really large. I'll demonstrate an example of that in this lecture. Before we can get to that function, we need to understand the notation in it. So there are 3 bits of notation. 2 are fairly straightforward. One's going to take a little bit of explaining. First off, the easy notation. We denote the probability of success in any one trial to be lowercase p. I know it might seem like it would be better to use lowercase s, but remember we've already used lowercase s for sample standard deviation, and s's kind of look like 5s, and so there are lots of reasons why s isn't a good choice for us, so we're going to use lowercase p, which is the traditional letter. The probability of failure in any one trial is denoted by lowercase q. Again, you might say, well, we should use f for failure, but we use lowercase f for frequency, so we just take the next letter in the alphabet after p. We call the probability of failure in any one trial lowercase q. We're going to see these 2 letters in the formula for calculating binomial probabilities. You're also going to see this notation that you might be familiar with, but not everybody has seen this before they get into a statistics course, so I thought I would cover it really quickly. The product of all positive whole numbers less than or equal to the positive whole number n is denoted by n followed by an exclamation point. I know my handwriting isn't perfect here, but that's supposed to be an exclamation point. And the way that we read that isn't with excitement. That's not n, but we say n factorial. Much less fun. It would be fun to go around screaming numbers all the time, but we don't. We call this n factorial. And again, the notation tells us to take the product of all positive whole numbers less than or equal to the positive whole number that's given here. Some quick examples of factorial notation. When I write 3 followed by an exclamation point in this context, that's not excitement, that's not 3, it's 3 factorial, and it means the product of all positive whole numbers less than or equal to 3. So I take 3 times 2 times 1, and that's 6. If I write 8 factorial, that's the product of all positive whole numbers less than or equal to 8. This happens to be the largest one that I have memorized. This is 40,320. Now, one thing some of you might have picked up on is that I've chosen to write in the ones, even though multiplying by 1 doesn't change anything. It is part of the definition because it's the product of all positive whole numbers less than or equal to the given number. And so by definition 1 is in there. But the reason I put 1 in there is because it allows us to see how we would calculate 1 factorial. 1 factorial says start at 1 and end at 1. So 1 factorial would be 1. And even though you might not care, I feel compelled to explain what factorials have to do with probability. Factorials give us a way to count things without literally counting them up. It's a counting technique that gives you the number of ways that something can happen without having to list them. So, for example, I calculated 3 factorial to be 6. It turns out that 3 factorial is the number of ways that you can arrange 3 distinct objects in order. So like if I had 3 objects, like a star, a circle, and a square, and I wanted to know the total number of ways that I could arrange those objects, well, I could flip the last 2, or I could put the circle first with the star second, or I could put the circle first with the square second, or I could put the square first, star second, circle, square, circle, star. And let's see, that's 1, 2, 3, 4, 5, 6. There were 6 different ways that I could arrange those objects. Rather than listing them, we can just tell that there are 6 ways to arrange them because 3 factorial is 6. The logic is we had 3 choices for our first symbol. Once we've chosen that, there are 2 choices for the second symbol. And once you've chosen both of those, there's only 1 symbol left over, and you multiply those together, and that gives us 6. And that might seem like a complicated way to do it when you could just list the 6 different ways to arrange the objects. But what if you had 8 objects? You don't want to list out the 40,320 different ways to arrange 8 objects unless you have a worse social life than me. So instead of making that list, we just calculate how many ways it can happen because that's what we need to know. So I'm going to kind of smoke and mirrors this. I'm not going to explain all of the nuances. If you want to know exactly how the factorials work into this function, you can read the text. It's enough for me to just let you know that factorials can be used to count the number of ways things can happen. And besides, we're going to be running to the calculator with this eventually anyway, and you won't have to do this subtle part by hand. It'll all be handled by the calculator. I do want to show you the formula though and run you through it a couple of times because I don't want you to think it's magic or something that we couldn't handle. So I'm going to demonstrate this function a couple of times. It looks complicated, but I want to remind you that eventually we're going to learn how to do this with the calculator. So no panic attacks when you see this ridiculous formula. Here's the formula that gives us the probability of a certain number of successes in a binomial probability experiment. It says the probability of exactly x successes in n trials of a binomial probability experiment is given by this monstrous formula. It says n factorial divided by the product of x factorial and n minus x factorial times p to the x power times q to the n minus x power. And here's a reminder of what those symbols mean. We use p as the probability of success in a single trial. We use q as the probability of failure in a single trial. And x is required to be a whole number less than or equal to n if you want to use this formula. X is the number of successes and n is the number of trials. You can't have more successes than trials. So x has to be less than or equal to n. And x has to be a whole number because you can't have half of a success. The number of successes has to be a whole number. So that's where these two restrictions come from. It has to be a whole number, and it has to be less than or equal to n. This formula isn't that hard to use unless the numbers are nasty. Remember that factorials grow really quickly. If n is big, then that numerator is hard to calculate by hand. P and Q are probabilities, and so they're going to be fractions or decimals, and putting exponents in fractions or decimals can be tricky if you have a nasty decimal or a big exponent. So this can be arduous to do by hand, but in simple situations it's not that bad. I want to show you that. I'm going to say this again, even though I know I've said it a couple times already. We're eventually going to learn a calculator function that will do all of this for us. We'll still have to be able to identify that the experiment is binomial, and we'll have to be able to identify the pieces that go into the calculator. We have to know what the inputs are, tell it what to do. But you're not actually going to do this math by hand for me. And I'm not just saying that you don't have to. I mean you are going to be forbidden from doing it by hand, and you are going to be required to do it with the calculator. But the math person in me just wants to show you that this isn't that bad and that we could do it by hand. It also gives you a little bit of insight to how it works. I don't want this to be a big mystery. So just a couple of times. Bear with me. Here's an experiment. It says a coin is flipped 4 times, and then we're asked to find a probability. Find the probability that the coin comes up heads exactly twice. Okay, this is binomial. Let's first talk about that part. This is a binomial experiment. We have a fixed number of repeated trials. We're flipping the same coin 4 times. Fixed number of repeated trials. Secondly, there are 2 categories of outcome because the coin can come up heads or it can come up tails. Classic example of 2 categories of outcome. And then the trials are independent of one another, and again, I don't need you to check that, but when you flip a coin, it doesn't matter what came up on a previous flip. Future flips aren't affected by that. So this has that independence that I don't really care if you check. Because this is binomial, we can use the formula on the previous slide to find probabilities. Let me transcribe it here. It's n factorial over the product of x factorial and n minus x factorial times p to the x power times q to the n minus x power. It's great if you have a formula, but it's useless if you don't know what these things are. So remember that n is the number of trials. P is the probability of success in any one trial. Q is the probability of failure in any one trial. And X is the number of successes. Now one of these is very easy to identify. We've actually already talked about it. The number of trials is 4. So N is 4. The others refer to success and failure, and that means that we need to decide which outcome we want to be a success and which outcome we want to be a failure. A general rule that I think will serve you well is to make a success the outcome that we're interested in, the one that's talked about in the problem. So this says find the probability that the coin comes up heads. So I would make a success when the coin comes up heads in any one flip. Now we can talk about P, which is the probability that the coin comes up heads in any one flip. Well, that's 1/2. Half the time it comes up heads and half the time it comes up tails. P will not always be 1/2. I'll show you an example of that. It's a common misconception is that because we've narrowed this down to 2 categories that they're each going to be equally likely, but that's not true. You already know that. We've already talked about it. But you might not be focused on that because you're looking at this nasty formula. Q is the probability of failure. Well, if the coin comes up heads half of the time, then the coin comes up not heads half of the time. Q has to be equal to 1 minus P because failure is the complement of success. So P plus Q always has to be 1. We'll see that in our next example as well. And the number of successes, well, we want it to come up heads exactly twice, and heads is a success, so X would be 2. And now we can just plug all of these in. And when I get all of the numbers in place, it looks nasty, but actually this isn't that hard to calculate. 4 factorial is 4 times 3 times 2 times 1, that's 24. 2 factorial is 2. 4 minus 2 is 2, and 2 factorial is 2. This is 1/2 squared, that's 1/4. This is also 1/2 squared, that's another 1/4. And now we can just multiply straight across and we get 24 over 64. And I'm going to reduce this just because we're going to check the answer in another way. So both the numerator and denominator are divisible by 8. And so reducing, I get 3/8. So the probability that the coin comes up heads exactly twice is 3/8. Now this one we can actually verify because we know another way to come up with that probability, and that's to write out the sample space. And I've done that for you on the next slide. I've taken all of the different arrangements of 4 possible coin flips and listed them. There are 16 total here, starting with heads on all 4 flips. And then I've got this list of 3 heads and 1 tail, and so on, all the way down to 4 tails. And we want to find the probability that the coin comes up heads exactly twice. Well, there are 16 total outcomes. And let's see, where are the ones with exactly 2 heads? Well, I've organized them so that they're all in this middle row. So there are a total of 6. And if we reduce that by dividing each by 2, we get 3/8, which is the answer we got on the last slide. And when I demonstrate this, your reaction might be, well, wasn't that a lot easier to do? Well, maybe for you, because you weren't the one who had to come up with these 16 different outcomes, right? I did that for you. And I'm not saying that was some genius thing that I pulled off. It was a bit time consuming, and that was just for 4 flips. Suppose I bump this up to even just 6 flips. With 6 flips, now you've got 64 different outcomes, each of which is a string of 6 H's and T's. That would take a really long time to write out, and then you'd have to hunt through it for the outcome that you're looking for. The formula would be faster in that scenario, and I'm going to keep selling you on this. Eventually, we're going to learn how to do this with the calculator. So then it's going to be much easier. We'll still have to do this work off on the right, where we identify the number of trials, the probability of success, and the number of successes. We won't have to identify failure, because if you tell the calculator the probability of success, it can deduce the probability of failure because of that connection of failure and success being complements. So we'll still have to do this stuff on the right, but we won't have to do all of this number crunching on our own. The calculator will handle that. So the formula will be the nice way to do this, as opposed to using a sample space. I've got an example with kind of a big sample space here. It says a die is rolled 3 times, find the probability of rolling exactly 1, and then I drew a picture of a 6 because writing 1/6 looked funny to me, but I'm saying that we're rolling a 6. Now the sample space for this experiment is going to have 216 outcomes because there's 6 different ways the first roll could come up, there's 6 different ways the second roll could come up, and there's 6 different ways the third roll could come up, and 6 times 6 times 6 is 216. And I like you guys a lot, but I wasn't going to write that out for you like I did with the coin example. So I found an image of it on Google, and this one had been used for some purpose, so it's got all kinds of circles and ovals and stuff on it. Ignore those. That has nothing to do with the problem I'm asking you to do. But you can see that it's really, really big, and coming up with it on your own would take a lot of time. But there is a sample space for this, and you could go hunting through it to verify our answer here. Rather than having to write all that out, we can find this probability using the binomial probability formula that we were just looking at. Before we just jump in using it, let's verify that this is binomial. I mean, it would be kind of silly of me to give this long speech and then have this not be binomial. So obviously it's going to be, but let's make sure. There are a fixed number of repeated trials because we're rolling the die 3 times. The outcomes of those trials can be classified into one of 2 outcomes because you either roll a 6 or you don't roll a 6. In fact, let's just take the time now to declare that our success is rolling a 6. Let's just get that out of the way. That way we can jump into identifying the inputs to that function. And then lastly, the trials are independent of one another because when you roll a die, it doesn't remember what came up on previous rolls. Previous rolls don't affect future rolls. Okay, so our formula is n factorial over x factorial n minus x factorial times p to the x times q to the n minus x. And we need to identify what those inputs are. So n is the number of trials, and we're going to roll the die 3 times, so n is 3. P is the probability of success in any one trial. So we've declared that a success is rolling a 6, and we know that on a 6-sided die, the probability of rolling a 6 is 1/6. One of the 6 outcomes is a 6. Q is the probability of failure, and failure would be not rolling a 6, and because that's the complement of rolling a 6, its probability has to be 1 minus the previous probability, so it's got to be 5 6. Remember that P plus Q has to be 1. X is the number of successes you're interested in, and in this case that's 1. We want 1 6. With the exception of coming up with Q, this is the skill that we need to have when we're using the calculator function that we're going to learn. So let's go through this one more time. N is the number of trials, and we're going to roll this die 3 times. That's the repeated trials part of this experiment. So N is 3. We've declared that a success is rolling a 6, because that's one of the 2 categories of outcome that we're interested in. What is the probability of rolling a 6? Well, it's 1 in 6. Because the die has 6 sides. Q is equal to 1 minus P, so even without context it's 5 6. But remember there are 5 sides on the die that aren't 6s, so that's why the probability of failure is 5 6. And then why is X 1? Well, X is the number of successes, and we're interested in the probability of rolling exactly 1 6, so X is 1. If this had said find the probability of rolling exactly 2 6s, then X would be 2. That's what we did in the previous example. We wanted to know the probability that the coin came up heads exactly twice, and that's why X was 2. Here we want to know the probability of 1 success, so X is 1. And the rest of this is just number crunching. Then you plug the numbers into the formula, and now you just have to do the calculations. 3 factorial is 6 because it's 3 times 2 times 1. 1 factorial is 1, we talked about that. 3 minus 1 is 2, and 2 factorial is 2. 1 6 to the first power is 1 6. Anything to the first power is just itself. This is 5 6 to the 3 minus 1 power. Well, 3 minus 1 is 2, so this is 5 6 squared. When you square a fraction, you square the numerator, and you square the denominator. And now, we could just multiply this all together, but unlike the first calculation, this one's going to be a little bit nastier. So let me do some canceling first. These 6's cancel. That way I can ignore those, and now I can just multiply across the top. The numerator is 25, the denominator is 72. If you want to get that answer from the sample space, then you'll have to go through this and count all of the outcomes that have exactly 1 6. And again, will that be hard? No, but it would take quite some time. And remember, you didn't have to come up with this sample space, and neither did I. I stole it from somewhere. But it would still take a while. And if we change this from 3 dice to 5 dice, well, now the sample space has 7,776 outcomes in it, and it would be too hard to use. We're definitely going to be fans of the formula, especially when I stop teasing it and I actually show you the calculator function. All of the examples that I do from here on out will be with the calculator function. We will not be using this formula by hand any other time in the rest of the class. So I don't want you to practice using the formula by hand. We're going to learn how to do this with the calculator. We're going to learn how to do more advanced things with the calculator. And not only am I saying that I don't want you to do any of these by hand, I'm saying it's going to be required that you do these things with the calculator functions. So I hope the expectations are clear. There's a skill that goes into using this formula that you will need. You have to be able to come up with this list of inputs, but you will not have to crunch these numbers yourself. You will not have to be able to plug into this formula. We're going to put those inputs into the calculator and let the calculator do everything for us behind the scenes. I would advise that you not try any practice problems or quiz problems until after you've seen the calculator function. If you have any questions about expectations or what you're supposed to take from this lesson, please don't hesitate to contact me.